Chapter 10 is on rotational motion, and the neat thing is, and I cover it this way, but all the stuff we learned in chapter 2 when we started learning about kinematics, we first learned that, for instance, the average velocity was the change in x divided by change in time. Oh, sorry about that. Change in x sort of, or change in time was average velocity. That was really average speed. The distance traveled divided by the time taken would be your average speed. But there's a vector quantity similar to that, which would be your displacement vector final minus your displacement vector initial divided by time taken. That gives the vector quantity that's your average velocity. And then we argued that if you let that time interval get smaller and smaller till you repeatedly get the same slope, despite getting smaller and smaller intervals, then you've reached a point where the velocity doesn't change much in that smaller time interval, and you've got the actual instantaneous velocity. That, of course, hopefully everybody recognized was a limit as delta t approached 0, which is a derivative. So obviously velocity is the instantaneous rate of change of the displacement vector with respect to time. So the dx vector over dt is your velocity. Then we argued that acceleration was your change in velocity divided by change in time on average. But if you wanted instantaneous, you again take the limiting process as delta t approach 0, and you got your instantaneous. Acceleration was dv dt. So again, that's a vector quantity. And then from that, we could integrate treating a as a constant, or in some cases, we did problems where the acceleration was not a constant. Maybe it was directly proportional to t, or maybe it was linear, or maybe it was squared. But the main thing is we could integrate a as if that's a function is equal to dv dt. We could integrate that and get an equation for velocity as a function of time. And if we had the initial conditions, we could even evaluate all the integration constants. And then we could, having velocity as a function of time and realizing that velocity is a function of time, if you take the derivative of that, you'd actually get the acceleration. But if you took the integral of that, you'd actually get the position as a function of time. And from that, we got x equals 1/2 at squared plus v0t. In the first step, when the acceleration was a constant, we ended up getting v equals v0 plus at. And then, like I said, once you'd evaluated that, you then knew v is a function of t. V of t is equal to v0 plus at. You put that on the left-hand side of v of t equals dx dt. And that allowed you to integrate again, and this time you got 1/2 at squared plus v0t plus x0. So those were your kinematic equations. We could eliminate time from the velocity equals velocity 0 plus at, and use that to solve for time, and then plug that in the x equals 1/2 at squared equation. And that gave us the v squared equals v0 squared plus 2a parentheses x minus x0. Well, it turns out with that same sort of rigmarole, you can do the same thing with rotational motion. The difference being that we're going to have a alternative version of velocity and an alternative version of acceleration, where our velocity was meters per second, for instance, for the units. In rotational motion, our angular velocity would be something along the lines of radians per second, or revolutions per minute, or degrees per second, or something like that. So there's a nice little parallel between those two, and that's what we're going to make use of. And it's so parallel that I don't feel too much inclined to solve a bunch of kinematic equations, but you can certainly do that because the equations are identical. So let me start off by sharing my screen and showing you the similarity between the linear motion and the rotational motion. Maybe I can stop yawning for a couple seconds. Nope, does not look like I can. Okay. So the first thing we had was we actually had that V is equal to, I don't know why I did that. V is equal to dx dt, at least in one dimension. Ultimately, that ended up being V is equal to, let's say, dr over dt, where r was supposed to be the position vector. Okay, and that could be a function of time and so on and so forth. And then we had A is equal to dv dt, like that. And of course, we were able to use those equations. I don't like how that just turned out. We were able to use those equations to find kinematic equations. And in fact, they were kinematic equations that could be in terms of constant acceleration. For instance, when we first integrated A equals dv dt for A equals a constant, we got V is equal to V0 plus AT. Then we tried setting that equal to V0 plus AT is equal to, remember that's velocity as a function of time, so that's dx over dt. And we could integrate that, and that gave us the x is equal to 1/2 AT squared plus V0t plus x0. Well, we can start off by realizing that from trig, we have this wonderful little expression where if this is the radius r and this is the angle theta, then this arc length from here to here, s, is given by r times theta. Now, if you remember, s is sort of the arc length. So if you take the derivative of the arc length with respect to time, that gives you a velocity. So in fact, you can get ds dt is equal to, and actually I should have wrote a different r there. Let me fix that real quick. Okay, ds dt is equal to r d theta dt. Well, it turns out this is essentially velocity, and this is going to be a new type of velocity we're going to call omega, and it's called the angular velocity. Now you can take dv dt is equal to r d omega over dt, and you're now going to get acceleration is equal to r times alpha. So in fact, we now got some new terms. Basically, you can call omega the angular velocity. And you can see the units would come out, for instance, from this equation, which can't be true unless this s equals r times theta and all this stuff can't be true unless theta is in radians. So this would mean angular velocity would have units of radians per second. And this one right here is called angular acceleration.
Didn't we use angular velocity to find out like how much friction is needed, or like what speed is too fast before a car starts sliding around a curve?
Yeah, we did that with mv squared over r, in other words. Yeah, absolutely. That was where I first introduced that omega, just putting it in there. And that is the same thing now. So now we have a relationship for that hopefully is going to make it a little more clear what exactly omega is and what exactly now, in this case, what alpha is, which you hadn't discovered before. So from this, we end up getting omega is equal to d theta over dt, which looks just like this equation right here. We also get alpha is equal to d omega over dt. It's a really bad looking dt I did there. All right, so we've got those. We also have, check this out, v equals v0 times at. Well, that's just omega equals omega 0 plus alpha t, and x equals 1/2 at squared. Well, that's just theta is equal to 1/2 alpha t squared plus omega 0 times t plus theta 0. And of course, when we solved this equation for t and plugged it in this equation here, we ended up getting v squared is equal to v0 squared plus 2ax minus x0. Well, guess what? When we do the same thing here, we end up getting omega squared is equal to omega 0 squared plus 2 alpha theta minus theta 0. So you can pretty much just make the translation of every problem you work, say from chapter 2 on kinematics. If you see something that's in meters per second, for instance, you can replace it with radians per second, and now you have the exact equivalent of basically rotational motion. And if it has an acceleration of meters per second, you're going to replace that, for instance, with a radians per second. Now, all of these equations will always work with radians, but to be honest with you, a lot of times it's going to work with degrees, or it's going to work with revolutions or cycles, that sort of stuff. But if you ever in doubt, just go ahead and use radians until you can figure it out yourself, or you can, make sense of it from the examples the book gives you. But all of this is just a rehash of the same stuff. So I very rarely do any additional kinematic problems in this chapter, just because we've already covered all that material. The more complex stuff is the new version of dynamics and the new version of conservation of energy. But you can already see that the synopsis is basically x becomes theta, v becomes omega, a becomes alpha. Okay. And in fact, you have a new equation that relates all these right here. A equals r times alpha, and v equals r times omega. And what I have to tell you is that this velocity is tangential. And this acceleration is tangential. So really, when you go to look at it, you could actually say the acceleration as a vector would be a tangential in, let's say, the t hat direction, and that's not to be mistaken with time. In fact, let me change that variable. Let me use capital T hat plus, then we'll have a centripetal acceleration, a centripetal, and that one will be towards the center, which I'll call C hat. Okay. And remember that little hat symbol just means, hey, this is going to be a unit vector. In this case, I called it C because it points towards the center of the circle. So center and circle both start with C, and T is tangential, which means it's actually, for instance, if the velocity was right here, it would be parallel to the surface at that particular point. So that's what that is. In general, that means the total acceleration is going to be a tangential part plus a centripetal part. And then you can also realize that alpha has another tangential part that, instead of having units of meters per second, it's going to have units like radians per second every second. Now, we've seen sort of what all the analogies are. X becomes theta, V becomes omega, A becomes alpha. But we haven't really considered dynamically what's going to happen. So I'm going to start that now. For instance, we had Newton's second law of motion, which I write with that sigma symbol to remind you that it's not a particular force that's on the left-hand side of Newton's law. It's in fact the sum of all the forces, and that's equal to m times a. Okay. Well, it turns out there's an equivalent or an analog to force, but instead of causing just linear acceleration, it actually causes a angular acceleration or a rotation. Does anybody know what the name of that kind of force type thing is that causes rotation? I'll give you a hint. There's a special kind of wrench called a blank wrench.
Is it torque?
Yes, that's the one. So this F equals ma is going to become the summation of the torques is equal to, now we're going to have an analog to mass, which is called the moment of inertia. And that's basically the reluctance of the object to actually rotate. As you could probably think, that will depend more on more things than just the mass. For instance, if you took a 100 pounds and you made it into the size of a BB, that might be a little that might be kind of difficult to rotate, but not too bad because it's really, really small. Now, if you took that 100 pounds and you basically put 50 pounds at each end of an 8-foot long massless rod, or maybe it weighs 10 pounds, say, and you put 40 pounds on each side, 45 pounds on each side, now that would be a lot harder to rotate. So you already see that this idea of making something rotate makes the mass depend not only on or makes the rotation rate not only depend on the mass, but also on how far it is from the center of rotation. So we end up writing I times alpha. And this guy right here is actually called a pseudo vector. So it's not exactly a vector. And your book talks about why it's not exactly, but basically it doesn't translate the same way from one coordinate system to another, for instance. It doesn't behave properly in that type of setting. So that's not why it's not really a vector. But the main thing is this thing introduces a new quantity called the moment of inertia. And in your statics class, they'll probably just call it the moment. And when you do a moment in there, it'll be quite different from the moment you get in class, in this class. In this class, I is equal to the summation from I equals 1 to n of m sub I times r sub I squared, where r sub I is basically the distance from the center of rotation to the location where m sub I is. So if you have, m1, then you figure out how far m1 is perpendicularly from the rotation axis to m1. That's r1. So you square that distance, multiply it by m1. Then you do the same thing for m2, and then you do the same thing for m3. Or if they're discrete, not discrete, but in fact continuous distribution, then it becomes the integral of r squared dm, which we'll use a little bit later, maybe even a little bit later today. Now you can see that from this, clearly the moment, the units of I are going to be kilograms, meters squared. you might recall, if I remember correctly, the moment that we deal with in structural engineering, for instance, which would be what you use in statics. If I remember correctly, it's like got units of inches to the fourth or some god awful thing like that. And that's basically because we're okay with talking about mass, but when you're talking about building a house or something like that, it's the geometry of it that they care more about, the geometry of the beam or whatever it is that they're trying to hold something up with. And they need the freedom to try different materials. So for instance, if I decide to have a beam hold up the roof above a doorway, I get a different strength if I use the lumber called SPF, which is spruce, pine, fir, than I do when I get, say, southern yellow pine or poplar or something like that. Or better yet, what if I use steel? I get an entirely different strength parameter. So if you try to pull out the mass part of that, that means more or less you're going to try to be dividing out the density, which relates mass to volume. And that can sort of make you see that, oh, if I divide R squared dm by the mass per unit volume, that's going to give you like inches to the fifth power there. So you can at least sort of see why the units are different, even though it's entirely different quantity. It is related to it. It's just a weird way that you have to deal with. The good news is it's actually pretty clear once you start doing it in statics. So now we've got one of the dynamic equations. But there was another version of Newton's second law. Does anybody remember what version of Newton's second law we covered last time? Can anybody state that for me, for instance? Sorry, Kevin. For instance, we got conservation of momentum from this equation. And does anybody remember what the condition was for momentum to be conserved?
Has to be fully elastic.
That was the kinetic energy one. But that is a very common mistake. So I'm glad you mentioned it so I could actually reiterate. Elastic collisions allow momentum to be conserved, but something else is required allow kinetic energy to be conserved. Something else is required for momentum to be conserved. Does anybody remember what I told you about what Newton really said when he stated his second law? He didn't state it as F equals ma. He stated it some other way. Does anybody remember what that was?
Momentum equals m times velocity.
There you go. You're closer now. It was F is equal to dp dt, where p was defined to be mass times velocity, a vector quantity. So that's the Newton's second law of motion. Well, we now know, for instance, that mass translates to moment of inertia. So you might be able to guess what Newton's second law is in that form. Anybody want to give it a try? I haven't yet defined the torque, by the way, guys. I will be doing that in a second. So the summation of the torque is equal to, anybody want to guess? It's a little unfair, really, to say it. But you might guess that there's something called the angular momentum, and that's actually true. And in fact, it would be dl dt, where L is called the angular momentum. Okay, now what is L? Well, first off, let me tell you what torque is. So it turns out torque, I think you can imagine, if I wanted to, say, loosen up a really big bolt, okay, it's got a buttload of strength someone's used to tighten it down. I can't get it loose. So would you like to use a little short crescent wrench, or would you like to use a really long crescent wrench to try to break that nut loose? Anybody have an idea?
Well, a mechanic's trick is the short wrench always wins.
There you go. So yeah, one way of looking at it is, and actually I never heard that. That's kind of funny. One way of looking at it is this is a hex bolt, for instance. That's supposed to be what it looks like. And you put a wrench around it like this. Well, it turns out when you're really trying to get a force big enough to actually rotate a nut, for instance, when I was doing my timing chain on my car, I ended up putting a wrench on it that was very long. So the wrench, for instance, was like 12 inches long from here to here. Then I put a breaker bar on that, which was a hollow steel tube that was 4 feet long. So I basically stuck the end of the wrench in there so it had enough overlap and put another 4 foot on there. And I put all my weight on it and I still couldn't break it loose. So ultimately, I ended up, and this is after trying impact wrenches and everything else, I ended up taking basically a wrench that was then attached to a breaker bar, which was 4 feet long. And then on the end of that breaker bar, my friend from a couple doors down was an AO chief. So he had, oddly enough, just happened to have a 6 foot long barrel of a gun that was mounted on a jet that I stuck in the end, and it was really nice hardened steel. And at that point, I literally had about 10 foot of lever arm. And still, I couldn't get it loose until I literally stood on it. And then my weight, which at the time was about 260, 270, my weight pushed it down enough to finally break it loose. Now, someone had obviously tightened it tighter than it's supposed to be. But the main point in all that is that you could probably guess the ability to rotate something is directly proportional to how far away from the center of rotation you apply the force. And that R that I use to indicate that can be called the lever arm. And we sort of think of it as a vector that points from the center of rotation to the point of application of the force. So now if I put a force, let's say right here, then you can see that the lever arm really does connect the center of rotation of the object to the actual point of application of the force. Now, you might also guess that this force can be put in such a way that it's really helpful, and then in another way where it's not so helpful. So for instance, if we broke the force down into that vertical component and that horizontal component, do you think that horizontal component is very helpful in loosening the bolt?
No.
No. Right. So in fact, it turns out if you were to move this force such that the force and the lever arm were tail to tail, this angle theta would be relevant. Can anybody guess what angle would be the best angle for theta if you really wanted to put the maximum amount of torque on a nut?
I'd guess 45 degrees.
45 is not too bad, but it turns out actually 90 is the best case scenario. So if you're actually at 90, notice that's all this force right here. Okay, so there's a lot of different ways to calculate torque. It turns out torque is equal to R times F times the sine of the angle between them. Now you can see, because sine maximizes at 90 degrees, you can see why sine is so helpful. You could also take and realize that this is in fact F, the component of F that's actually perpendicular to the lever arm. So I could write it as F perp times R. but I can also write it as torque is equal to R cross F, which is what we saw by seeing RF sine theta. I already said we could do F perp times R, but we can also do R perp times F. And it turns out there's different problems depending on how you are given the information. Different problems make different formulas better to use. So for instance, if you consider that F is this force that I drew down here in red, right, then you can see that the R has a component that is in fact parallel to the force, and then it has a component that's in fact perpendicular to the force. So in fact, this would be R perp, and that's the one that's helpful, just like this can be F perp, and that's the one that's helpful. So those are all the different ways you can calculate torque. Torque is equal to R times F. Oh, and by the way, I should remind you that in fact, R cross F, at least in magnitude. Let me not do it that way. Is R times F times the sine of theta is equal to the magnitude of the torque. Okay. Now, just for completeness, I want to point this out to you, and hopefully you already knew it from your trig part of pre-calculus. But if you, for instance, had, let's say you had F here and you had R here, then you can actually create a parallelogram like this. And it turns out that R cross F is actually equal in magnitude to the area of that parallelogram. And in fact, the vector R cross F is perpendicular to R, and it's perpendicular to F as well. And obviously its length is equal to the area. So that's some of the neat stuff we found now about torque. And now I can continue with my equations. So we already had, for instance, omega equals omega 0 plus AT, and theta equals 1/2 alpha t squared plus omega 0 times t plus theta 0. Now we have also that might help if I'm not writing with an eraser, that the summation of the forces, or excuse me, the summation of the torques is equal to I times alpha, and the summation of the torques is equal to dL dt, where L can be written as R cross P. So that's another version of the angular momentum. But again, remember, we also had P in linear motion. Actually, let me write that in black since I was sort of doing that. Since P is equal to M times V, what do you think the rotational analog of P equals MV is? So I'm thinking of L now giving me a magnitude. And what I realize is that momentum in linear motion was basically mass times velocity. We also noticed, for instance, that the summation of the forces is equal to mass times acceleration. That and this are equivalent, right? So what's analogous to mass in rotational motion? How about what's analogous to A in rotational motion?
Torque.
The torque is the analog to force. Remember, you have to use a force to cause an acceleration A, and that's why you get the total force is equal to M times A. Similarly, you can't use a force to rotate something. You have to use a force plus a lever arm, which gives you torque, which is what you just said, right? And we see on this F equals ma, the left-hand side is the total force. I'm arguing that the left-hand side is the total torque. But look at the right-hand side of F equals ma. You got mass times acceleration. What do you have on the right-hand side of torque equals blank blank? What's that on the right?
The angular speed.
Yes, closely related. So you say momentum is mass times velocity. So the analog to velocity is angular velocity. What's the analog to mass? Maybe this will help you. So what you're thinking about is comparing this equation right here to this equation right here. Actually, I don't like that. I'm going to use a different color. Let's use red. So we see this side is just like this side. So what's equivalent to mass right there?
Inertia.
Inertia. There you go. So when we look at this, we should expect M to be replaced with I. Actually, what I'll do is I'm going to write this back in blue. So we should expect M to be replaced with I. And what do you think you're going to replace V with? Someone's already said that, by the way.
Angular speed.
Exactly. So that's the omega. Okay. And that turns out, just by analogy, happens to be right. Okay. That's the magnitude of it. And in fact, remember when we used the summation of the forces is equal to DL, or excuse me, is equal to dP dt. That was the version of Newton's second law that Newton actually gave us. We found that when the summation of forces is equal to 0, then dP dt is equal to 0, which basically told us that the P had to be a constant. And that's what we mean by conservation of momentum, is P is a constant. So you can see from this that when the summation of the torques is equal to 0, then dL dt is equal to 0. So again, angular momentum is conserved in this case when we have a net torque equal to 0. So all of this is just a new way of looking at the same stuff, only we're now using different quantities with, slightly different units, so on and so forth. There's some more stuff. For instance, we did, let's say we had kinetic energy. was 1/2 mv squared. Anybody want to take a guess what kinetic energy is in the rotational world? I'll give you a start. 1/2.
Is it times inertia?
Yes, times inertia. And what do you think is going to be squared?
Angular speed squared.
There you go. Exactly. See how you can just guess by the former, equations. You can see what compared to what and get exactly the right expression. So it turns out that when an object is actually, say, rolling down an incline or something like that, and then you have kinetic energy total would be equal to 1/2 the mass times the velocity of the center of mass squared plus 1/2 the moment of inertia about the center of mass times omega squared. So that's the total kinetic energy. Oddly enough, we also had work is equal to the integral of F dot dl, which you can sometimes sort of think of simply as just F dx. Well, guess what? It turns out that work would be equal to the integral of torque times d theta. So there's another formula. So all of this stuff has the exact same analogies from variable to variable to variable, and you can make pretty much any equation you want just by doing that. The big differences are, like I said, the units are different. So now that we've sort of covered basically everything for that matter, what I want to do is solve a typical problem, which would be like a complex Atwood machine. So first off, let me show you a moment of inertia calculation because we're going to use that for the actual conservation, or excuse me, for the actual Atwood machine. So let's imagine for a second that I have, let's say, an axis. We have a z-axis this way. We have a y-axis that way. And we have an x-axis this way. So this is my x-axis, this is my y-axis, and this is my z-axis. And what I'm going to do is I am going to imagine a cylinder like this, whose radius is in fact r, whose thickness is in fact h, and whose mass is big M. Now what that means is the density, which is mass over volume, would be equal to M over pi r squared h. Okay, so I'm imagining this being a uniform mass. In other words, if I cut any part off of the cylinder, and let's say its volume was 1 millimeter by 1 millimeter by 1 millimeter, and I weighed it, if I cut any other part off of this mass and cut it down till it was 1 millimeter by 1 millimeter by 1 millimeter, then that would have exactly the same mass. Or if you did 2 millimeters by 2 millimeters by 2 millimeters, then that would have 8 times as much mass, and so on and so forth. So that's what I mean by a uniform body. What I do know, though, is that the moment of inertia of this would equal the integral of r squared dm, where r is the distance from the rotation axis, which, by the way, is the z-axis. So r would be the distance from the z-axis to any particular mass, and then dm would be that particular mass. So what I'm going to do is I want to calculate this integral, but in doing so, I need to make sure that the integrand, the r squared, doesn't vary by very much over the entirety of the dm, because if it did, then I'd have to like take an averaging process and all that stuff. And that's just not something I'm interested in doing. So what I'm going to do is imagine a shape that could help me. And the shape that comes to mind is basically a little ribbon whose inner radius is R and whose outer radius is R plus dr. So we're going to imagine this coming all the way down to here. Imagine this coming all the way down to here. So if you remember doing this like from your calculus class, you probably would have realized that this little thing, this little mass right here, dm, is actually equal to rho times dv. That's just from the definition of density. Density is mass over volume. So if you multiply density times volume, then you'll get the mass. Now, in this case, hopefully you realize this sort of looks like a rectangle. And what I mean by that, it looks like if you cut this little red sliver right there, and then down here, and then back up there, then what you get is essentially a rectangle whose length in one case is 2 pi r, whose thickness is dr, and whose height is h. Notice it's not exactly a rectangle because you can see right here that that's a little bit of a triangle. In fact, this length right here is not 2 pi r, but rather 2 pi times r plus dr. So you could actually do the calculation and figure out exactly what that volume is by taking a cylinder of radius r plus dr and then subtracting from it a cylinder of radius r. So dv is technically equal to pi times h times, let's say, r plus dr squared minus r squared. That's really what we're talking about here. Now that dr went to crap, so. So that's really the calculation. If you took time to do that, what you'd see is if you ignore terms of the order of dr squared or dr cubed or something like that, you'll still get basically the volume of this dv is approximately equal to 2 pi r h times dr. And that's what we're going to use. So now I can say, all right, well, looking at this as if the x-axis or the y-axis, say, is how far I am away from the z-axis, then I can just say this integral is going to be equal to x squared times 2 pi h x dx times rho, because rho is the density, of course. So you can see that when I do this, basically the 2 pi is a constant, so that can come out in front. The h is a constant, so that can come out in front. And the rho is a constant, so that can come out front. So now I'm going to have the integral of x cubed dx from x equals 0 to big R. I think that integral is pretty easy. I guess y'all can figure out what it is. It would be 2 pi h rho L to the fourth, or excuse me, R to the fourth. r to the fourth over 4. Of course, that is equal to pi h rho over 2 times r to the fourth. But now we can use the fact that the density is m over pi r squared h, and we'll get pi h over 2 times m over pi r squared h times r to the fourth. And I think you can see what happens. 2 of these are going to cancel out, leaving a 2 there and canceling that one out completely. This h is going to cancel out completely. This pi is going to cancel out completely. And I am, in fact, just left with 1/2 mr squared. And that is, in fact, the moment of inertia for a cylinder. So I cylinder is equal to 1/2 mr squared. And that doesn't matter if the cylinder is h units tall or if it's just a flat circular disc. So for instance, if you had this, the moment of inertia for this guy would also be 1/2 mr squared. Okay, again, assuming it's rotating about that z-axis. All right. Now, if you look in this week's module, you'll see I've actually put a video. I think I've maybe put 2 or 3 links of me deriving formulas for the center of mass, or excuse me, for the moment of inertia on it. So you can check those out. But that's just a quick version of me doing that. Now I'm going to use that to actually solve an Atwood machine problem. So the Atwood machine problem is basically, let's imagine, for instance, that we have a pulley, but this time the pulley actually has a mass. And in fact, I'm going to say the pulley is a cylinder. Okay. And well, I don't know what that last thing was, but there you go. So something like that. It's actually just gonna, actually, that's just crap. I hate that. I hate everything about that. Okay. So it has a radius r, it has a mass m, okay? And therefore I can figure out what its moment of inertia is. And hanging from this side will be a mass m2. And hanging from this side will be a mass m1. Now, in this case, I think you can see if I pull down on m2, or if I just think about from the perspective of m2, m2 feels like it's falling and would say, oh, I should be accelerating at about 9.8 meters per second, but that rope is slowing me down. So according to m2, it feels a tension pulling up on it. And m1, as m2 is falling down, that rope is going to the right, and that's lifting m1. So m1 thinks it has a tension on the left-hand side that's pulling it up as well. So that's how you're getting those two tensions. But in fact, the two tensions have to be different, because the tension that m2 is feeling is big enough to not only lift m1 up, but it's also big enough to rotate the cylinder. So we're going to have different actual tensions. So first off, I'm going to draw a free body diagram. So here's a solution. Now this is an Atwood machine, so I think you know that means that I want to know what is A. And now, since we're dealing with rotational motion, I also want to know what alpha is. And I want to know what the tension on the left is. And I want to know what the tension on the right is. So first off, I'm going to draw a little mass right here. This is going to be M1. And it looks to me like the way I drew this, I'm trying to tell you that M2 is going to go down and M1 is going to go up. So I'm going to call M2 going down being the positive direction. So what that's going to do is force this force right here to be in the positive Y direction. And in fact, it's going to be a force equal to M2 going down. So let me change this to M2, not M1. So this is M2. What I said was Y going down on the right-hand side is the positive direction. So this will be M2G. And in fact, acting in the opposite direction would be the tension T right. From Newton's second law, that tells me that, in fact, M2G minus T right is equal to M2A. Now, if M2 goes down exactly 1 inch, then M1 is going to go up exactly 1 inch, and a point on the edge of the actual spool or the pulley there is going to move 1 inch as well. So you can see that there's no reason to subscript A. It's just going to be the exact same for the left-hand side, the right-hand side. And in fact, if there's strings not slipping, the pulley should rotate by just as much. So I'm going to call this equation 1. And now we know why we don't have to actually have a subscripted. Now I'm going to draw another free body diagram. I've already decided that the thing on the right going down is the positive direction. So the thing on the left going up must be the positive direction. So what I'm going to do is I'm going to draw a free body diagram right here. That's going to be M1. This is going to be my y-axis. And in fact, this is going to have a tension T left acting on it. And then this is going to have a force here equal to M1G. So Newton's second law of motion in this case gives me TL minus M1G is equal to M1A. And I'm going to call that equation 2. And now I have 2 equations. Notice I have 4 unknowns, so technically you'll need 4 equations. Now, the free body diagram for the pulley is actually not too terribly bad. What we're going to do is I've already decided that the right-hand side moving down is the positive direction. So I'm going to consider the torque on the right-hand side the positive direction. So what I'm going to say is right here is a tension T right. And then right here is a tension T left. And notice it's actually, these tensions are actually perpendicular to the lever arm. So the T times R times the sine of theta is just T times R. So I get equation 3 from the summation of the torques equals I times alpha is going to give me, in fact, R times TR minus R times TL is equal to I times alpha. Now, I already know what the moment of inertia is for a cylinder, so I can go ahead and write this as RTR minus RTL is equal to 1/2 M R squared times alpha. And you can see, in fact, that that is going to cancel out with these R's. And now I just got 1/2 MR. But in fact, or MR times alpha, but R times alpha is actually equal to A. So I can actually make this equation now into TR minus TL is equal to 1/2 M times A. And I've already used what would have been called, say, equation 3. And that's the fact that the rope is not sliding along the pulley. So A is equal to R times alpha. This will be equation 4 right here. Let's write that in blue. That'll be equation 4 there. So first off, what I'm going to do is I'm going to take and solve 1 for TR, and that's going to give me TR is equal to M2 times G minus A. And then equation 2, I'm going to solve that for TL. And that's going to give me TL is equal to M1 times A plus G. Okay. And now with that, I can call this 1 prime and I can call this 2 prime. I'm going to plug 1 prime and 2 prime into equation 4. That's going to give me M2 G minus A minus M1 times A plus G is equal to 1/2 MA. Now you can see I only have one unknown here. It's just A. So let me distribute all this. I'm going to get M2G minus M2A minus M1A minus M1G is equal to 1/2 MA. Now I get all the A's on one side and everything else on the other side. So I'm going to take this and I'm going to say this is M2. That takes care of that guy. Minus M1. That takes care of that guy. Times G is equal to, now I'm going to pull M1A to the right-hand side and M2A to the right-hand side. Both of them are negative right now, so that means they're going to become positive. And I will have M1 plus M2 plus 1/2 M, all that times A. So now I know that A is in fact equal to M2 minus M1 over M1 plus M2 plus 1/2 M. All of that, which is unitless, by the way, so that's kind of nice. You get rid of this M, it didn't turn out too pretty. All of that, which is unitless, can be multiplied by G, which has obviously the units of acceleration. So I've now solved for the acceleration. I can use equation 3 to give me that alpha is actually equal to A over R. I can use equation 1 prime to get TR. And I can use equation 2 prime to get TL. And I'm going to let you guys do this for extra credit. Because we're just about out of time. Actually, we've got about 16 more minutes, so that's not too bad. But I'll let you do that for extra credit either way. I think you can see what we're going to do, though. Obviously, the alpha should be pretty easy. You're just going to divide this expression for A by R. So literally, you could just say the same thing and put a R, capital R, under the G. Now, what you're going to do with that is, now that you have A, you can plug it right in here for A in that and get a common denominator and simplify it. And then you can do the same thing for A right here again, getting a common denominator and simplifying it. And what you should be able to see is that in the special case of big M equals 0, notice that's a massless pulley. That's what we've been solving before we covered torque. If I put big M equal to 0, I should get the old Atwood machine answers. So if big M goes to 0, then A should go to the Atwood machine, which was M2 minus M1 over M1 plus M2 times G. You can see that already did it, right? You can also see that the tension, which was 2M1 M2G over M1 plus M2, that's what the Atwood machine should be. If you set the M equal to 0, your T left and your T right should both be equal to that. So I'll say and. So that's something for you to compare. You can turn that in. I'm going to put an extra credit link on this week's module, and that should help you. Anybody have any questions about that? Okay, so now I have shown you some of the stuff we can do now that we have torque and an equation for torque. One thing I want to warn you about, and your book does this too, it makes the author make sure he tells you this equation right here that's not always true. In fact, in order for that equation to be true, you either have to have a fixed axis of rotation. So that's one criteria. So if the axis of rotation is fixed, it's not moving, then and it goes right through the center of mass, for instance, then this equation applies. The other option is the center of the axis of rotation goes through the center of mass and is always through the center of mass. If that's the case, then it works again as well. But any other cases, it's not going to work. So that equation only works in those cases. So make sure you keep that in mind. Whereas F equals MA works all the time. So there's other problems we can solve. For instance, we can take, let's consider Home Alone. Y'all remember the movie Home Alone? So in Home Alone, what Kevin did was basically he put a bunch of cans of paint on the end of a rope, and when someone walked down, the cans of paint would swing down and hit them. There was also one part I want to say where a sledgehammer came down. So we could imagine the sledgehammer like that. So let's take, for instance, let's say a rod of mass M, okay, uniformly distributed. So a uniform rod. And let's put a little hinge on it so that gravity is free to act on it. So what we learned in the last chapter was that basically the purpose of the center of mass is, or one of the things we can use the center of mass for, is the center of mass is where an object behaves as if forces are acting on it. So if this object were hanging, for instance, from a ceiling, then the center of mass, if this length right here is L, then I'd go over to here, which is L over 2, and that would be the center of mass. And in fact, gravity acts like it's acting right there with a force of mg. Okay. What I would like to know is what is the velocity of the end when the rod is vertical? Okay, so that's our question. Well, and this is one of those cases where the summation of the forces is actually equal to, or the summation of the torques is actually equal to I times alpha. And in fact, we're going to do it like this. We're going to say the solution is the summation of the torques is equal to I times alpha, like this. Now, in order to do this, we actually see that there is a rotation point right here. And that's what it's rotating about. Now, there's something called the parallel axis theorem. That says basically the moment of inertia about any point, let's say, is equal to the moment of inertia about the center of mass plus m times h squared, where h is the distance between the center of mass to the center of rotation. Okay, so in this case, h is equal to L over 2 because that's how far away the center of rotation is from the center of mass. Now, we can actually calculate what the moment of inertia of a rod is. So actually, let's go back to blue. So I rod about the end, I can calculate it straight up like that, or I can use the parallel axis theorem, is equal to integral of r squared dm. What I'm going to do is I'm going to imagine dm is just rho dx. So I'll say integral x squared rho dx. And that basically points off to any distance. Let's say I draw it like this. There's my y-axis. There's my x-axis. This is my dm, which equals rho times dx, right? And then clearly this distance from here to here is just x. Now the rho in this case is just going to be the mass of the rod divided by the length L. In other words, we're actually not using rho, we're using what we normally call lambda, and that's just fine, okay? So I'm going to say rho times the integral of x squared dx is going to give me rho times 1/3 x cubed from 0 to L. So that's going to be equal to rho times 1/3 L cubed. Well, now I'm going to plug in that rho, quote unquote, the density. Again, this isn't really the density, it's the density per unit length, which I told you guys earlier was really lambda. That's going to be m over L times 1/3 L cubed. That's going to give me 1/3 mL squared. And that is the moment of inertia about the end. Now, if we did it for the rod about the center of mass, what we'd have to do is we do the integral of x squared rho dx, but we'd integrate from negative L over 2 to L over 2. And I think you can see that you'd get rho times 1/3 L over 2 cubed minus negative L over 2 cubed. which becomes, in this case, we're going to say rho is m over L times 1/3. Now this is going to be L cubed over 8 minus a negative be plus L cubed over 8. So we get m over L times L cubed over 8 plus L cubed over 8 would be 2L cubed over 8, which would be L cubed over 4. So it'd be 1/12 L cubed. So about the center of mass, we expect this to be 1. Let's make sure I got that right. 2 over 8 would be 1/4. 1/4 times 1/3 would be 1/12. So it'd be 1/12 ml squared. So the parallel axis theorem implies that I about the end should equal 1/12 ml squared, because that's the moment of inertia about the center of mass. And then plus m times the distance between it and that is L over 2. So that's L over 2 squared. I should have wrote that in red. Plus, oops, did it again. Plus m times L over 2 squared. So this would be 1/4 L squared plus 1/12 L squared. So 1/12 plus 1/4 ml squared. Well, 1/4 is the same thing as 3/12. So 3/12 plus 1/12 would be 4/12, and 4/12 of course is 1/3. So we get 1/3 ml squared, which is exactly what I got before. So yes, that does give us our moment of inertia. Now that I know my moment of inertia, I can just write Newton's second law for rotation. And what we're going to get is the summation of the torques is equal to I times alpha. In fact, there's really only one torque acting on it, and it's the gravitational torque. So we end up getting, in fact, that the torque, if I draw the object like this distance from here to here is L over 2. We've got a force of M times G acting on it there. And then at any time later, we basically have this thing making an angle theta, this being mg, this being theta as well. It turns out that to get the torque right, you have to have a component of the force that's parallel to the lever arm, and then a component of the force that's perpendicular to the lever arm, which is this guy. So F perp is going to be M times G times the sine of theta. So what we're going to write is M times G times the sine of theta is the force, but the torque is that times L over 2. All of that is going to equal the moment of inertia, which we learned was 1/3 ml squared